So let me just pop up to a general theme, I think, which is in common between some of these kinds of demos and some of the things that I think everybody was talking about, which is the value of motion, both things moving around in the world, but also your own motion as an agent. That was sort of Stefano's point, and Bill and I were talking with him afterwards, and I think we both had the reaction that we liked a lot of the things you were saying, but we felt that it's not just about your own motion, but about the fact of things moving. And Shimon made the point that that's very fundamental to the way infants first come to these concepts like intentional agents and their hands and gazes and so on. So I mean, maybe that's another theme for more work in this field, is how much we might want to consider motion as a source of structure and what makes a good representation. You had a yeah.
I haven't seen the frame version, but my question looking at those writings is that at some point I can see it.
Yeah. So it pops out at some point.
But not because, is that because you're moving or because there is a nice view?
I tried to make sure there wasn't any one nice view.
Okay.
Yeah.
So there's no nice view, so there's motion actually.
For most of them, there's no one good view, like in the end. Yeah.
Okay.
That's right. But right. That the motion was essential. And I'm not sure. I didn't actually try like background subtraction. I don't think simple kinds of background subtraction would work either. But who knows? Maybe. Yeah. There's a question back there.
Yeah. Just how much do you think the words are? Because like here we are talking about manifold deep learning. Like, is there the context?
Sure.
A lot?
That could be part of it. Yeah, definitely.
For us being able to read that.
What do you think?
I think you're. I mean, it's text. We're very good at this.
You're probably right. I showed it to my daughter last night to pilot it, my 10-year-old daughter, and I don't know if she knows what a manifold is, but she had no problem reading it. So, okay, good point. But I guess what I wanted to say, I mean, what the reason why I positively responded to your question is context and understanding that language has meaning is not unrelated to our ability to solve some of these problems. I don't think we have to be necessarily primed by deep learning. I mean, I think she also got the deep learning one thing, and for better or worse, she doesn't know what deep learning is.
I think the question you were asking was this image is not whether you can read the text.
Yes.
Just a way to test
Yes.
it, but it's whether you can interpret that there's waters, there's a cheese grater, whatever.
So I mean, Stefano, do you think, for example, that the kind of general mathematical framework you were presenting could be also applied to these kinds of invariances, or Tommy, do you think?
Depends on what the task is. So
Well, so let's say you want to, this is also a question for Tommy or Lorenzo and really anybody here. To what extent do you think your mathematical frameworks for invariance could apply to these cases? Should they? How would they?
Apply to characters, for instance.
Right.
The dictionary examples you showed after this.
Yeah.
So when the database is available.
Oh, you mean the handwritten characters ones?
Yeah.
No, that would be great.
Josh, you might want to look at whether or not you know the language. It's not just the characters. You'll recognize something like manifold.
Well, that's one of the, in this case, it was one of the nice things about the data set we have for the new characters is
Right.
you don't have to know the language. In fact, some of those are even made up. Nobody knows
But I
them.
think you have a hard time reading deep learning in a language you don't know.
Oh, sure.
Even if it were the same
Yeah.
alphabet.
Yeah, I think it'd be interesting to combine to do the one-shot character learning in a new alphabet with this kind of variance. Could you recognize that character underwater? I think you probably could. I think it's part of why I want to echo a theme that Alan made, or highlighted, compositionality, right? It's something we've both learned from Stu Gieman and others. I think, unless, there's so many causal processes that are involved in generating the data that we ultimately see, and unless we represent those in a way that's compositional, and I think that requires the generative model, right? The discriminative direction is not compositional, at least as I understand it. Though Tommy started to convince me yesterday that maybe it might be. Maybe that's a question for you guys, is to what extent, and maybe some of the stuff Alan talked about at the end, to what extent can you make a bottom-up kind of discriminative or just bottom-up feed-forward model whose compositionality, that sort of inherits the compositionality in the generative direction in the bottom-up thing. I think if that's going to work at all, it's got to do something like that, probably, right?
Okay, so I got to comment on this. I think those are the notion of generative and sort of reasoning models, etc. are orthogonal. So you can have you can have a model that can give you several interpretations for a scene or whatever that is completely discriminative. it will require to have some process of minimizing some energy function or maximizing some likelihood. So we could think of this perhaps as feedback, not purely feedforward, but it's not necessarily a generative model. The best example of this are speech and handwritten recognition systems that are trained discriminatively. They're not generative models. They're trained purely discriminatively. They don't manipulate probabilities, but they will give you a score for every possible interpretation. They're not strictly feedforward, right? And now, on the side, you can also have generative models that are, models that try to explain the input. And Alan was trying to tell us that those could also be feedforward. I'm not sure I believe this, but
no, some of them are. That's definitely. Yeah.
well, so I guess it depends on the definition of feedforward. So so there are models like the ones I showed yesterday of the autoencoders where the encoder actually implements some sort of inference algorithm. And so if you unfold them in time for long enough, they look like a feedforward model, but in reality, the best way to look at them are iterative energy minimization algorithms. If you unfold them in time, of course, you can look at them as feedforward processes. So there's no kind of clear boundary. Well, this one actually goes from the input to the output, so it's not. It's an encoder that actually computes the features from the input. It's a decoder that regenerates the inputs, and this one is simple. It's actually just a linear encoder.
Let's see, this is the engineer speaking. Let me speak.
I think that is a compliment.
What Josh was saying, I think our brain does use generative models at some levels.
I didn't say the opposite of that.
No,
I was trying to define terms, right?
That's the brain at all.
No, I was trying to define terms. Let's say, it's not necessary that.
But you refer to machines.
Not necessarily. Just general processes of what you mean by generative, feedforward, discriminative, etc. You can have, inference that's essentially discriminative and still has, multiple interpretations and does complicated inference. It doesn't have to be generative.
There's a question.
I think, going back, for instance, to what Shimon said, vision, human vision, is not just discrimination or recognition. It's much, much more. And, whether you call it generative or not, I think of it as generative in some sense.
Yeah, so something like causal explanation, right? Like Shimon's nice example of drinking, right?
Yeah.
Like in what sense are all of those examples of drinking? Well, like drinking is just the best explanation for what you are seeing there. There's an agent doing something, and what are they doing? They're drinking. They're trying to get liquid into their mouth, basically.
Feedforward models, to my view,
Yeah.
are doing what a visual system does in the first 100 milliseconds, which is very, very weak.
Yeah.
I mean, it's very important to get it at least 50% right, but it's not vision. It's just pointing at some keywords on the image, some places you may want to look more, and not much more than that.
Yeah, I agree with Tommy. I think that the second stage is maybe quite different from the first stage. You use many more very class-specific features and very class-specific relation, whether this is longer than this and between the other two and things like this, which are not going to compute all over the place. We found that with drinking, people are very sensitive to whether some images we thought were drinking, and then people said they were not drinking, the people were toasting, and it turned out we had images that we thought that were a database of drinking. In the drinking, there were people doing this, and when we showed it to subject, we were very sensitive. They said, this is not drinking, this is toasting, and then we tilted this 20 degrees like this, and people were happy that this is drinking. Now, I don't think that you compute all the possible relations between all possible linear features in the scene, as in your bottom up, and then you feed it all these values into a classifier. But once you are in a particular situation, you become very sensitive to measuring particular features. So my overall picture of the architecture is you have this feedforward, it gives you good candidates for various things to look more carefully into. So in the case of drinking, it will not give you drinking, but it's a person and there is a hand and maybe an object in the head and so on. and then you run something more like a particular routine that extracts exactly the things you need, various relations, various features, and it makes the final interpretation.
Can I say just something?
Attention is very vague. Some attention is you're very attentive, you're relaxed, I don't know, but it's more, I would say, class specific, and you extract certain relations when you need them, where you need them, where you cannot afford to compute all of them.
Well, I mean, can I say something? It could be routines, which I like, or probabilistic inference. I think either way it poses a strong constraint because both the feedforward and this type of top-down processes are in Cortex, the same architecture, the same machinery. But and so, maybe the back projection are more involved in the second part than in the first one. But it's an interesting.
And whether you want to call it DDMCMC or sequence seeking with streams and counter streams, right? The idea that they might interact in a deep and interesting way, that the feed-forward one might be essentially trying to generate the hypotheses or the burn-in for
80% of the circuitry cortex is support what comes after the first. Okay.
Well, I guess I sort of hedge my bets two ways because I'm on the DDMC type proposal paper, but also on the compositional thing. But I would still, argue with Shimon a bit because, okay, suppose I'm finding that this angle is important. If I throw out all that orientation information as I go up to do invariance, then yes, then I have to do a visual routine to get it back again. But it seems to me, at least with that particular thing, I can do what I was describing in my talk. That representation is available at the top level if I just want to know where the thing is. The details are not there, but if I do care about the details, I go down further down. So I could have within me automatically computing all those all the orientations, enough information to do it. And so if I want to get it, I'll go down there, but it doesn't mean that you'd have to run something new to do it.
Partly it's first of all you have to go back down. It's important, at least for the cortex, it probably involves the top-down, the feedback, because some of the relations you want to compute to make the final decision may be fairly fine, it's sort of depending on some small angles and lines represented better at V1 and V2 and you want to go down there. And the second point is that sometimes you want to know if something is the middle of the two things or closer to the right or closer to the left, whether something is longer or shorter than something else. So you cannot compute all the shorter than in between. Just unlikely that you're computing all the explicitly all the things that may be needed for the final decision on the way up. I think they are triggered once you have initial interpretation. I agree that probably you look at the image, you get certain things right, and you get certain things more ambiguous left. Based on this, you can trigger your additional computation that will get you the final interpretation. I think biologically, I would not be surprised if very often they have to consult things which are represented lower down, 2 maybe, or V4, or something V1 to make the final decision based on high resolution data.
I would say there's probably a trade-off. All I'm saying is I'm pushing the trade-off more in one direction. And that, I'd say certainly there's some things which even with the compositional things I think hard to do without sort of having the model and putting it down, but I think you can go perhaps a lot further than people are saying. When you go up, you don't sort of throw out the invariant, you sort of keep it around and you model it.
You want to get in? Yeah.
Yeah, this is probably related to the discussion. So I wonder if it wouldn't be the most efficient way for, especially in this ambiguous, efficient way, to look at the relations of objects, because as you said, most things are easy to say. But for example, yesterday there was this demo, and you have something like a pen on the table. It could be a letter opener, it could be a pen, whatever. The shape is pretty similar, but based on the relations, what's also on the object, what's there, what's in the scene, I make a decision about what's the most likely thing to do. If I would only look at the shapes of the features of the object, of course this is much harder. So in a way, moving up into a relational domain probably is like from propositional
this is like Alan's quote of Stu Gehman that low-level vision is ambiguous, but high-level vision isn't. Is that partly what you're getting at also? Yeah, I mean, I think there's all sorts of interesting ways in which the higher level, more abstract problems might be easier, and also might be learned earlier in development. This is a point that we had an interesting discussion at this last summer's CogSci conference with Shimon and Liz Velke, who's one of the leading people studying infants' cognition and perception, and also Noah Goodman, who's got this nice phrase, the blessing of abstraction. It's very interesting in infants that it's often the concepts that they learn first are, and they can recognize most robustly in scenes, are these very abstract things like an agent or an object, before they can tell the difference between a pen and a toothbrush, or a letter opener, or a sea urchin and a cauliflower, or whatever. Like things that, a lot of the machine vision community has been, from an application and engineering point of view, reasonably focused on, and a big data perspective, reasonably focused on. Infants are not interested in those things at the beginning, but they are interested in using patterns of motion to understand, to parse the scene into objects and agents and their interactions. And I think that's really telling us something important. Like, I really liked Jan's talk, almost every part of it, except for one bullet point where you said, where I disagreed with, on the CogSci side of looking at, how do we learn more abstract concepts or build more abstract concepts on top of less abstract concepts. I mean, that is interesting, and certainly that's one part of human learning. But another important thing, which I think is at least as relevant as anything to vision and going from low to high level vision, is looking at how early infants seem to learn these very abstract things. And then maybe, as Alan's point, how quickly we might be able to recognize the more abstract high level concepts, and then use that to actually fill in the gaps in the low level stuff, rather than just going from low to high level in our learning and our inference. Anyway, go ahead, Jan, you have
So I think to address that question, it's useful to look at people have done in other contexts. So I keep coming back to this speech recognition and handwriting recognition. So those ideas of doing fast recognition in the low level and doing sort of reasoning for the high level to take into account things like language models. People in speech and handwriting have been doing this for about 20 years. And there's a good handle on this. Now we call this CRF, and it's been sort of reinvented in different contexts. But the right way to do this is you have sort of feedforward kind of thing that extracts categories, features, whatever you want to call them, and then you have some sort of model where the inference consists in minimizing some energy or maximizing some likelihood, and which gives you essentially a score for each possible interpretation of the inputs, and that could use models that model the context, like language in the case of speech and handwriting. And that comes on top. So that sort of jives with what some people are referring to here, where you have the fast process that does the low to mid level stuff, and then the kind of reasoning that is on top. And we know how to train these all from end to end. We've known this for over 20 years. So it's not a conceptual question. It's not even a question of whether it's the right thing to do. We know it's the right thing to do. It's just a practical question.
I would say, I mean, I think it is a good reflection of the state of the art in some of the best computer vision that's trying to solve the problems that I talked about here. Like, some of the best capture breakers. There's a paper from a few years ago by Malik and colleagues, which basically does that, right? It has a sort of bottom-up detector pass, and then has some global constraints with a language model that it enforces in using some kind of mixed integer linear program. Or similarly, like some of the best current work that's in sort of mainstream machine vision that tries to do problems like this. Like I'm thinking of some of the CMU group stuff, like Marshall Herbert and Derek Hoyne. Marshall Herbert and Derek Hoyne, who's not there anymore, but did some of this really nice sort of like Block's World revisit stuff, right? They basically do a similar kind of thing. There's kind of a bottom-up pass, and then there's a sort of a enforced global physics constraints and something like that. It's different from what we've been doing in these things, where we basically it's sort of full-on, top-down physics guided interpretation. And I think somehow we like to understand how those kind of things might relate. Like, might the strategy that you're saying that has worked really well with speech and handwriting recognition, and that more and more people are using to get from low to high level vision, an initial detector pass subject to enforcing global constraints, how might that, is that going to be a suitably good way to do this kind of inference in a general purpose way? Part of why I show demos like these and spend a lot of time thinking about these is I'm not so sure it might be. But I think we need to push that approach beyond things like even like those simple captchas or simple Block's World scenes where you can see in the image most of the evidence for each of the objects, like Alan's 2 out of 3 rule. I think those are going to be sort of key test cases, because for that approach to work, all the objects have to be mostly detectable by the bottom-up cues. But part of the point of things like these is that they aren't, right? At least in any one static frame. Maybe in motion, if we can handle motion in the right way, they are. But I guess the general point I'm trying to say is, let's see if we can look at these cases where, the key test cases for that approach are going to be ones where, on the surface at least, it's not clear that there's enough bottom-up information for that first pass to get you most of the way, and then have the top-down pass kind of just clean it up and fill in the details. Other comments? Questions?
So I was wondering how fast people think your ability to detect someone drinking would be. So if you did kind of one of Thomas' RSVP sequences with a mask and looked at reaction time, do you think there's that much inference that's going on? Because I would guess that people could try very quickly tell you.
Yeah, I think that's right. I mean, right? You probably know that the RSVP paradigm is basically everything.
Right. People did not write with the RSVP. My guess would be that it's likely that they will be confused between similar things like drinking and toasting, for example, because this may require some additional stage to make the disambiguation. They will get it within a restricted class, but they will need more. But still, the entire thing is pretty fast. You will need to really RSVP. It may cost you additional 30 milliseconds or something like that.
Right. I mean, would that be enough time for all these kinds of inferences to happen?
It will be fairly quick. But yeah, my feeling is that it will require an extra step. It will be possible to demonstrate.